So we're now going to start transitioning into PDEs. So yes, it is a little bit ironic that there's a word OD on the board, but it means ode. What's an ode? A poem, a lyrical poem? Well, right? Is that what it is? Yeah. Well, I really happen to like the second derivative. It's my favorite. And I think it'll become your favorite too. And the reason why it's my favorite is because, as I may have mentioned before, it's responsible for life. It's responsible for life on this planet. Without the second derivative, things would either explode or die. It's thanks to the second derivative that there is motion as we know it, and therefore life. So a lot to be excited about, but here's what I mean specifically. So the second derivative comes up in applied problems from the physical world all the time. So the one place you're familiar with it showing up is in Newton's law, F equals ma. And a is, of course, the second derivative of position with respect to time. So one example that we've considered was the harmonic oscillator. And I'll just give you a little bit of a glimpse of what would happen if the second derivative was unimportant. So when we look at a harmonic oscillator, it's u double prime. So let's put it this way, equals minus whatever times u. Remember, it was square root of k over m. Well, omega was. You would have here k over m. And we know it's a positive quantity, and the square root of it shows up in sines and cosines, so we're going to call it omega squared, the natural frequency. And so we know what this system does. This system oscillates with the natural frequency, thanks kind of to the second derivative. The way I wrote it right here looks like an eigenvalue equation, doesn't it, a little bit? It says that the second derivative, a linear operator, applied to the function, is some number times that function itself. Now, it's not quite an eigenvalue equation, because in an eigenvalue equation, this part is unknown. So we'll actually get there, we'll probably get there today where the analogy would be complete. We would end up with an equation like this, but this number will be unknown, and then it's just like an eigenvalue equation. Now, this is a little bit different because this number is given by the problem. And so it's helpful, and it will come up again today, that the eigenvalues, eigenfunctions of the second derivative operator are sines and cosines. We also have exponentials. But if you put an exponential here with a real exponent, you will get a positive number, right? If you imagine e to the 5t, you would get 25. If you imagine e to the minus 5t, you will once again get 25. So you don't get exponents here, even though they are also eigenfunctions of the second derivative operator. You get sines and cosines, because this number right here is negative. So the second derivative helps right there, so that's a good clue. We'll come back to it. But now suppose also that this harmonic oscillator, mass on a spring, was in honey or molasses, a very, very viscous ambient environment. You can kind of intuitively tell what will happen. You will pull it and let go, and it will just slowly go to the equilibrium. Well, what are the equations that describe it sufficiently well? Well, you have to add friction. And what is friction? It's some force proportional to velocity. So it'll be something like minus, what usually denotes friction? Is there a common letter? B. How about R for resistance? Because it might be viscous resistance, viscous forces, minus R u prime. Okay? So if this happens in air, or the table has a little bit of friction, the spring will oscillate, but the amplitude will decay, and it will eventually, or will it, stop? Well, the decay will be exponential, because you know how to solve this sort of thing. You will get a complex number with a real and imaginary part, even though we haven't talked about complex numbers before. And so it'll have an oscillatory component. And it will also be dying down exponentially. So it will theoretically never really stop, but the amplitude will decay very rapidly. Now let's imagine a situation where R is very, very large. Back to our honey scenario. What will happen then? Well, we know what will happen intuitively. We could also solve this system with a very large R, and we'll discover that we just have two positive roots, and so we just have exponential decay. But there is a slightly different way of looking at it, how a physicist would look at a system like this. A physicist might look and say, if R is very large, then this term is very small compared to this. And so you would just skip it. Okay? And then you would end up with U double prime equals minus RU prime. And this is the sort of thing that you can integrate once, because both sides are a derivative. And so you'll basically end up with the first order equation. U prime equals minus RU plus some constant. Okay? And now we're left with a first order equation. In other words, we lost our second derivative. We lost our second derivative. This is a little bit vague for a math class. But the point that I want to make is mathematical. If you have equations with only the second derivative, if you have equations with only the first derivative, all you can possibly get is an exponential, because you will have one real root always. And if the physics was right, that root will be negative. In this case, it will be minus R. So all you can possibly get is e to the minus RT plus some constant. And so an equation like that represents death as opposed to life, right? Slow and painful death. And that's all you could really get if you only had first derivatives in the world. There could be a situation where this term comes with a different sign. For example, population. If you say that population grows at a constant rate, that with every generation it gets multiplied by a factor of R that's greater than 1, then you might end up with a system with an equation like this. U prime equals RU. Okay? And the solution to an equation like this would be e to the RT, exponential growth. That's all you can get with a second derivative, either decay or explosive growth. In other words, explosions. So neither scenario, in my opinion, represents life. I'm being a little bit overly dramatic for no reason. But I'm just trying to say that, thank God that there are second derivatives which give us a little bit of stability. Things don't die, things don't explode, things tend to oscillate. And that's what happens when it's a second derivative with respect to time. Now let me tell you a few words about the second derivative with respect to x, or with respect to a spatial variable, and why that's responsible for life. So again, okay, so it's maybe not responsible for life, it's responsible for, let's say, music. So if you imagine a guitarist with a guitar, that's what they do, and you have a string, think of the string as a function. So if I'm just holding my guitar, then it's a constant function. Very boring, right? Doesn't make a sound. Now I can lift the guitar up or down. In other words, I'm changing the value of the function. And you agree with me? That does nothing musically. Whether the guitar is here or up here makes no difference. So the absolute position of the guitar makes absolutely no difference. So that's the value of the function. What else can I do? I can change the slope of the string, right? I can take the guitar and turn it. Or if you're Paul McCartney, you do it like this. Okay, I was going to not laugh. Does that change anything? Does that make a sound? It doesn't make a sound. So changing the slope doesn't make a sound. Changing a slope doesn't change the equilibrium. You can do the same, you can follow the same analogy if you're just holding a metal bar. There are some things it doesn't really resist. It doesn't resist where it's placed. It does because of its interaction with gravity, but not because of itself. There are no internal forces. It doesn't resist the change in slope. There are no internal forces that arise when you just change its slope. So the value of the function itself and its first derivative don't matter in this case. But if you bend it, in other words, if you change the second derivative, then the bar responds, probably with very strong internal forces. And these forces are restorative. They want to return it, restore it to its original configuration, which was probably being straight. The same thing happens with a guitar string, right? When you pluck it, you change its shape. You change its second derivative, right? You need to reach the second derivative in order for the body to want to return to its original configuration. And that's what happens to the guitar string. You displace it, you change its second derivative in shape. So u will now have a derivative with respect to x. And do you see how we've, just like that, transitioned into partial differential equations? We're now talking about things like bars and strings, whose evolution is a function of time, but it's a continuous body. So there's a different evolution at every different point in x. So u is now a function of t and x. And very soon, very soon it'll be x and y, and z if you want, or any other set of variables. Okay? So you displace the string, but you don't just displace it. You very much change its shape because it's still fixed at the ends. So you've imposed a non-zero second derivative. And then you let go, and the string comes back. And it overshoots. Why does it overshoot? Well, it overshoots because the second derivative causes a force. Do I have F equals ma? I don't. F equals ma. Always a privilege to write this down. F equals ma. So when you displace the string, change its shape, you've imposed a force on every part of the string due to the change in shape. And so you've imposed acceleration. And then the string begins to accelerate, and by the time it reaches its approximate equilibrium configuration, it has already picked up some velocity. So it overshoots. This would not have happened if we were stuck in the world of first derivatives. If this was a first derivative, if your guitar was stuck in molasses, the string would just come back and there would be no sound. It's thanks to the second derivative that it overshoots, goes approximately the same distance to the other side, and so it begins to oscillate. So this oscillation, the onset takes place in the first place because of the second derivative with respect to x. And the evolution continues because of the second derivative with respect to time. So you need both of them. And that's where, on an intuitive level, you get the wave equation. So that will be, surprisingly, our first partial differential equation. And let's consider the case of a guitar string. Here we are. This describes it perfectly. U is the displacement in the y direction. So let's call this axis x equals 0. And this function describes the displacement of the point at x at a time t. So initially, let's say, before you pluck it, before you even do anything to it, it's 0. And then you will displace it. It might become something like this when you're displacing it. Okay? Right? Does that look about right? If you use your finger and not a pick. If you use your pick, this will be a little sharper. And it's kind of a coincidence that we call that sound a little sharper, crisper. Right? So that little corner that you might create here makes a huge difference, especially early on. And we'll talk about it, why it really matters early on and not later. These simple equations and simple analysis holds the answers to all of those questions. Initially, it sounds crisper, and then a quarter of a second later, you can't even tell how the string was plucked. And so this function would be at a time t, u of x. So it's a function of both t and x. Did I describe pretty well what u is? Right? So if you fix a moment of time t, you're only left with u of x. And then it describes the shape of the guitar string at that time t. And so it becomes a function of x. And so you see how right there, it's very different from the harmonic oscillator, where there was only 1 degree of freedom, or from 20 planets, which is 60 degrees of freedom, but still 60 discrete degrees of freedom. Not an infinite amount, right? Can I use the word infinity in this case, kind of? Right? You can kind of think of it as an infinite number of degrees of freedom, because at every point the string can theoretically be anywhere as long as it's continuous and maybe smooth. And that changes everything, because there is now interaction between neighboring points. Interaction in the sense that you can take a derivative, you can describe a shape. And so we will now consider a single point. Again, this is a math class, not a physics class. We just got to write down an equation. And we'll say that, again, only appealing to your intuition. I'm not pretending to derive any equation in physics. I think Newton and Euler will turn over in their graves if what I'm about to say can be considered as a derivation of an equation describing a phenomenon. You have to do it at a much deeper level. I just want to argue that what I'm about to write down kind of makes sense. There are other much more profound considerations why this makes sense. So we'll say that it wants to return, that there is a force that makes it return. So instead of writing mass, I'll write density, because we're considering just one small point. I could write the mass, but again, that would get a little bit too physicsy. So we're at this point. It has a density rho, and then we have to have the second derivative. So it will be d. We will eventually use different notation, but we need the second derivative of u with respect to t squared. And this represents the acceleration of this point. Acceleration back towards equilibrium. It always accelerates towards the equilibrium because the force is always a restoring force. It always acts back towards the equilibrium. When it reaches the equilibrium and overshoots, well, now there's a force bringing it back. So this is mass times acceleration, and it equals, well, there would be some coefficient of proportionality, because the string can be more tight or less tight. So the tighter, the greater the coefficient. So let's call it K, sort of by analogy with spring. And then it equals, well, we've discussed, it can be the position itself. The string doesn't care about its position. The string doesn't care about its second derivative. It's the first derivative, because that's slope. It's the second derivative. Curvature. Curvature is proportional to the second derivative. The degree to which it's not straight, that's what matters. So it's proportional to the second derivative. And here is our first partial differential equation. And this one is called the wave equation. We're still in the middle of my ode to the second derivative. I'm not done with glorifying the second derivative. It's just that it's very nice to write down an equation that has second derivatives all over it. There's a second derivative on the left because it's acceleration, and there's a second derivative on the right because it represents the restoring force. The two sources of life. Question? That's a very good question. So when you're talking about a partial differential equation, the paradigm shifts entirely from ordinary differential equations. This equation is valid at all points from 0 to L, whatever the length of the string is. It's valid, this condition is valid at all of these points. So you can think of it roughly as infinitely many conditions, one for every point x. So I kind of wrote it down for a typical point, but it applies everywhere. This differential condition applies everywhere. And if I were to formally draw the domain of the definition for this problem, for an ODE, it was just a straight line, a segment. And it was actually almost felt simpler than a segment because it was basically one point at a time that just keeps evolving, so that it's really almost like a point, kind of. Really, formally a segment, intuitively a point. So formally here, this is u is a function of two variables. So it now happens on a domain like this, where in x, it goes from 0 to L. And in time, it goes once again from 0 to some capital time t. And this is where u lives. U is a function of t and x. In this simple case, lives on this rectangle. And this condition applies at every point on this rectangle. So we're looking for a function of two variables now, where if you picked any point and you evaluated its second derivative with respect to x and its second derivative with respect to time, you would find out that they satisfy this equation. And how would you go about solving this equation? Well, because you know of the problem that it came with, you would of course start here and march forward. So your solution definitely in some sense sweeps across this domain up, because time goes up. All of this is roughly speaking, right? But the paradigm have changed completely. And maybe it's a little bit hard to explain all of the details all at once. So you'll just see as we go along what it means to solve a PDE. And it's not like solving an ODE. There is no such thing as a general solution and then satisfy the initial conditions. It's a project every time. A very, very fun project, but still a project. Okay? So does that make a little bit of sense? So let's consider a little bit with a second derivative. Well, I actually think an interesting question here would have been to think about the sign. Is it really that this could have been a minus, right? Because it's the second derivative, but how do you know that it points the right way? Well, you really have to think it through. If the string is bent down, the second derivative is positive, and so the acceleration is up. So it has to be proportional to the second derivative as opposed to minus the second derivative. So that's why there is a plus. Always important to think these signs. If this was a minus, this would be an entirely different equation. There are fancy words that describe the flavor of the equation. And I don't expect you to remember this, but in its current form, it's known as a hyperbolic equation. And if this was a minus, it would be an elliptic equation. And the way you approach it changes 100%.